So, test is on Thursday. I'm doing this for Kelly and the other people that weren't here because of band. Or you'll be kicked out of class, one or the other. All right, so on Tuesday, we talked about redox, but remember, I went through that pretty quickly. The redox reactions, I went through pretty quickly. And as I was going through them, I knew you probably might catch some stuff, but most of it might be a little hazy by the end of the class. But what you'll notice is if I at least talk about it once, the second time I talk about it, it tends to sink in a little bit better. So I knew that you probably wouldn't fully understand it after the first day. That's why I'm going to go and revisit it today. So, yeah, thank you. So I'm going to, I added some stuff yesterday to the slide. So first I'm going to copy it over to y'all's period. Now, this is the old one, I think. Nope. This is the old one. So what we talked about, 3 different reactions that occur in solution. So 3 different reactions that occur in solution. Now, the first one was precipitation. That one utilized the solubility rules. That was the big idea on that one. The second, the acid-base reactions, you really had to think about the difference between strong acid and weak acid, strong base and weak base. And the whole goal was to write those net ionic equations. And so we went through writing net ionic equations for those 2 types of reactions that occur in solutions. The third type of reaction, redox. Now, how is redox different from the other 2? There's something that happens in a redox reaction that the other reactions don't have. Electrons are transferred. So redox is like a overall term that you can place on that reaction. But if you were to zoom in, you have really 2 like sub reactions that you can think of, or really terms. One process is called oxidation, one process is called reduction. In the future, you'll be able to write half reactions, what we call half reactions, or half cells. And but here we're just going to think of it holistically. So we're just going to write one equation because they're really not hard redox reactions. They're just single displacement reactions, but also redox. Oil rig was a way to remember what oxidation was and what reduction was, the difference between the 2. So oxidation is loss, reduction is gain. So got my wireless tablet so I can talk in this and write at the same time. Now, you could also remember the difference by Leo. The lion goes grr, but most people don't like that one. I kind of like this one better because it's less words you have to say in your mind. Oil rig. Now, another way you can remember which species is being reduced or which one's undergoing reduction is the substance that's being reduced also reduces in charge. So if I'm looking at an equation and I'm trying to determine which substance is being reduced, I just look at all the oxidation states and I see which one reduces in charge. That one is what's reduced and the other one's oxidized. I'll go over an example of that in just a minute. So we keep going down. Now, in order to identify which substance is oxidized and which one's reduced, you need to assign oxidation numbers to your substances. We talked about that, and I warned you, some of it gets kind of weird on some of the substances. You're used to halogens having negative charges, and all of a sudden, when they're bound to oxygen in a polyatomic ion, they will take on positive charges. It's weird. It's a little uncomfortable, but it's true. Like Your manganese will have all different types of charges. I've seen it have +2, and I've seen it go all the way up to +7. And then I told you about cobalt. So cobalt, +2 and +3. We're going to do a lab with cobalt when we get to equilibrium. And just changing that one electron causes, I guess, the light to be absorbed differently. And then you get two different colored solutions. One is a light pink color, kind of like my shirt, or maybe that shirt. And then the other one's a dark blue shirt, like Atabe's shirt. So that's where that phrase cobalt blue comes from. And I'm pretty sure, I haven't checked on myself, but I'm pretty sure it feels right. Cobalt +3 is the blue colored one. Now, oxidation numbers. So most of the oxidation numbers, determining oxidation numbers, are easy and straightforward, like elements in their elemental form. Elements in their elemental form always have a charge of 0. So oxygen, it's a neutral compound. Chlorine gas, that's chlorine in its elemental form, 0. You're going to see in your book problems that arsenic has the elemental form As4, which is not something you see pretty often, but that is one, they call it allotrope of arsenic. Sulfur, I've seen sulfur as S8. So that's a sulfur in its elemental form. It's like a ring. We call allotrope of sulfur. But these are all elements in their elemental form. It would have an overall charge of 0. Now, if I have, let's say, chlorine not as a molecule or in its elemental form, but as an ion, then the oxidation number here for chlorine is 0, but here it's a -1. Yeah.
What about metal by itself normally?
So a metal by itself, like Na by itself,
Yeah.
would be 0. Na in solution, ion, +1. That's why I'm revisiting this, because I knew y'all didn't fully grasp what I was saying. So the oxidation number of a monatomic ion is the same of its charge. Those are easy. Like this right here, that's a monatomic ion. Monoatomic, one atom. This is not an ion. Okay, Na, that's just sodium metal. If I were to have a metal and I put it in front of you, that's sodium metal, which I don't have and I don't want to buy. Chlorine ion, -1. That's a monatomic ion. We could come up with a bunch of them. Aluminum ion, sulfur ion, bromine ion, rubidium ion, potassium ion, sodium ion, magnesium ion. Get it? Monatomic ion. All right? Your polyatomic ions, or the ones that typically are the hardest to kind of figure out, because you have to do a little bit of math, which the math isn't hard. Now, if, let's say I have oxygen, and there's like a few little hints you can kind of remember. Oxygen tends to always have a -2 charge. Like 99% of the time, oxygen is going to have a -2 charge. It's the second most electronegative element on the periodic table, with fluorine being the most electronegative element. Fluorine's stubborn. It's always going to be -1. Oxygen, -2, but it's less stubborn. Sometimes it can be -1. Sometimes it's not as stable as when it's -2, but if it's -1, that means you have a peroxide ion. So if I said peroxide, that would be just so people can see what I'm doing. Peroxide would be O2 with a -2 charge. So this is think of it as a polyatomic ion. So if I have 2 oxygens with the overall charge of -2, what's the charge of each oxygen? -1. Okay? So 2 times -1 is -2. So if I have hydrogen peroxide, sometimes you have to recognize that it's a peroxide. If I have H2O2, I quickly recognize, oh, this is hydrogen peroxide, because I know that hydrogen has a +1 charge, and I see a subscript of 2 down there. It just doesn't match up. So you're going to have a problem in your book where it looks like this, K2O2. And you just go on your knowledge of potassium, and +1 is not matching up with the subscript. So that tells you, oh, okay, what this really is potassium peroxide. So if you were being asked for the charge of oxygen, it would be -1 here. Okay, I'm going to scroll down and we're going to do a book problem. Number 49. This is how you would see a question being asked in the book about oxidation numbers. Now, once again, you're doing all this because in a reaction, you might have to figure out which one's being reduced and which one's being oxidized. In order to do that, you'll have to assign oxidation numbers. So, let's just do A. So A is saying, determine the oxidation number for the indicated element in the following substances. So I need to find the oxidation number of S in SO2. What's the overall oxidation number for this compound? It's a neutral compound, so 0. If it were an ion, then it would have a charge up here, but it doesn't, so it's a neutral compound. So what? Okay. Now I told you 99% of the time oxygen has what charge? -2. So therefore, sulfur must have a +4. So that's kind of how I work those out. -1.
It could be peroxide salt, right?
Oh, this is, when you have peroxide, typically you're going to have it, I know these kind of get weird, but you're going to typically see it with a metallic ion, unless it's hydrogen peroxide. Oxygen -1 and sulfur 2. Because this isn't peroxide. It's just SO2. You just kind of have to, and this is weird. Oh, are you being sarcastic? Oh. There's an element of educational reasoning in here. And just after working so many, you just kind of get better at it. Peroxide is, you'll see it bound to a metallic ion or hydrogen. So COCl2. Now, if I were to draw this just for the heck of it, it would look like this. So carbon double bonded to oxygen with 2 chlorines. If that kind of stuff makes you happy, which it makes me happy drawing stuff. Now, my overall charge here is what? 0. So carbon is bound to oxygen and 2 chlorines. We have 1 oxygen with a -2 charge plus 2 chlorines with a -1 charge. Therefore, carbon has to be +4 for that one. Huh? Well, I think of this a little bit differently because it's a molecular compound. It's not like it's a polyatomic ion. So it's all molecular. Yeah. Yep. Yep. Yeah. All right, part C, MnO4. So this is a polyatomic ion, MnO4. Now, knowing what we know about polyatomic ions, we have manganese and oxygen in there. Which one of the two is going to assume a negative? Oxygen. So I told you 99% of the time oxygen is what charge? -2. So my overall charge is -1. I've got 4 oxygens with a -2. That leaves manganese with a charge of +7. All right. I'm going to let you do D, E, and F. Nah, I'm just going to let you just kind of not know. Okay. You can do whatever your heart desires. I don't care. Exactly, yes. Maybe like in part F. Yeah. Mm-hmm. Potentially. See, there's always exceptions, so there could be an exception to the 99% rule. There's always an exception to the 99% rule.
So 99% of the time, 99%.
And usually it's depending on how I feel. How y'all doing over there? Good. T Hooks. Well, he likes to be called by Terrell. Do you want me to call you T Hooks or D Hooks? T Hooks. Here's Terrell. T Hooks. He's easily. Hey, are y'all doing D, E, and F? What? Yeah, Ise. C. Okay. All right. BRO. That reminds me of a student I used to have. This one kid that I had in my AP class, he was also in AP Environmental, and I went with on the environmental trip to Cumberland Island. Oh my gosh, that kid, I can't tell you how many times he said, "Nah, bro." It was constant. So then on the next test, I put it as a joke, sodium hypobromite. Um, nah, bro, like, or I forgot how it went, but it was a joke. So every time I see BRO, I think of him. Nah, bro, sodium hypobromite. He liked, and then I taught his girlfriend the next year, so I kept the joke on there, and then told the whole class again about her boyfriend. And then I told y'all just because it's, yeah, yeah, okay. I don't say names. It's just the story is where, okay, we gotta move on. Nerd alert. All right, D. Y'all checking? I'm writing as they just continue. Yeah. Oh, I'm sorry. I just wrote it wrong. I was probably looking right here and then they were talking about stuff. That happens. Yeah. Huh? Y'all are still, are you over there still trying to figure out who it is? You don't know anyone? Not one person? All right. Now I'm going to do one equation, number 54. So these are redox reactions. I had a choice of whether I wanted to work some from your net ionic sheet or if I just want to start it on the book problems. I want to start on, and I chose the book problems because I figured if I at least started working some for you, it would kind of open up the door, to you wanting to maybe start working some as well. Sometimes that happens. Like the net ionic sheet, I worked a couple for y'all, and then the next thing I know, people are coming to me with all of them worked out. So it does work. My strategies work. So, number 54 is saying write the balanced molecular and net ionic equations for the reactions of hydrochloric acid and nickel. This is a single displacement reaction. And I told you, single displacement reactions are basically redox. So if I were to write this out, HCl plus Na, I'm going to get H2, hydrogen gas, any acid with metal, and then just because I know this is the common formula for nickel plus 2, I've got nickel 2 chloride in the back. It's actually a nice neon color solution, kind of like that binder right there, that color. It's really neat. Now, the net ionic equation, HCl, remember I start on the left, work my way to the right. This is a strong acid, so I'm going to break that up. Hey, yes. H plus Cl minus 1 plus nickel yields H2. This is a soluble salt and 2 chlorides. Y'all see that? 2 chlorides. What did I forget to do over here now that I'm writing that out and I see? Balance it. So 2 HCl turns into 2 hydrogen ions, 2 chlorine ions. This is where people from last period got a little confused. Does nickel solid, is that the same thing as nickel ion? No. If I start off with a piece of metal nickel, and I put it in acid, it's going to look like it's starting to dissolve away, but it's really not dissolving, it's reacting. And that nickel is going to start going into the solution as an ion. So you're going to start having nickel ions roaming around the solution. So in the beginning, the solution is going to look clear, but in the end, it's going to start turning a greenish color because you have these nickel ions going into the solution. All right, it is not the same thing. I cannot cross out metal nickel and nickel ion. Those are not the same. They need to look exactly the same. And there's only one substance that looks exactly the same, and that's chlorine ion. Yeah. Redox. Yep. Only in redox you can do that. So, yes. Well, here you have hydrogen ion that's turning into a hydrogen neutral hydrogen molecule. So, redox. Yeah. Yeah. Yes. That's also a covalent molecule. So you're kind of referring back to oxidation number? Sometimes you can assign, like, you have substances actually do have an oxidation number, and then you assign what's called like a formal charge, which we'll learn later on. So it's not necessarily the oxidation number, but it helps you to identify which substance is being oxidized and reduced. So some of the oxidation numbers really are the oxidation state, and other ones are just kind of assigning these, we call formal charges to the elements just to help us identify the process of what's going on. Does that make sense? Right. Yeah.
So when the hydrogen and the hydrochloric acid breaks, it has
Why did it break?
ion
Why did it break?
because it dissociates.
Why? Why?
Because it's a strong acid.
It's a strong acid. All right, continue your question.
So after it dissociates, the hydrogen pulls
Wait,
out.
does it fully dissociate?
Yes,
Okay, good. Why?
because it's strong acid.
Yes. All right, continue your question.
So the hydrogens both are lacking one electron. That's why they're plus one.
They're not lacking. They're just chilling. They're yeah,
They're just chilling with one less electron, and then when they combine,
but there's two of them chilling.
yes,
There's two hydrogen ions.
So I have two fingers up. So
Okay.
so then when they combine together, instead of having
So when nickel is hanging out in the acid, then you're going to have these hydrogens that come along on the surface of the nickel metal, and there's a transfer that occurs. I have a video that I can show you. Here's the zinc, but this is not an acid. This is actually, pretend like you have a piece of iron metal, and it turns into rust. That in itself is a redox reaction. So oxygen in the air, there will be a reaction that occurs at the surface of the metal, and that's redox. So the same with zinc. So here we go.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating
At the surface.
and zinc ions.
Whee,
We
whee.
say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand,
All right, let's think about this. What's the charge of zinc here? 0. What's the charge here? +2. What's the charge here? 0. What's the charge here? -2. So stuff is changing in charge. That's how you know it's redox. Huh? Zinc, yes. Zinc gives up the electrons to oxygen. No. In a net ionic equation, you're just showing the specific reaction of what's going on. So you kind of take out the spectator ions. Here's the actual reaction. So that's why you leave ions as ions and solids as solids. Yeah. No, that's molecular oxygen. Whenever you see O2 with a negative 2 charge, that's peroxide. Huh?
Isn't that what charge that?
Yeah. Yep. I already have done tutoring sessions. You just chose football over tutoring sessions. But yes, I'll have more in the future. It's okay, T-hooks. I don't, it happens. But I'll have more in the future, yeah.
Oxygen is said to be reduced because it gains electrons.
The end. Does that help you at all? Okay. We are behind because y'all have a ton of questions. But they're good questions. I'm going to move on to dilutions, and I'm going to go through this pretty quickly. So I need y'all to hold the questions for now. If I have a 500 milliliter graduated cylinder, and I say 500 because typically if I'm going to go through making a diluted solution or diluted acid, I'm going to use a larger graduated cylinder so I can make it one time for all my classes. Would make sense. So here's a 500 milliliter graduated cylinder. I'm going to use this to dilute acid. Let's say I'm diluting hydrochloric acid. If you buy hydrochloric acid in its most concentrated form from Flynn Scientific, is usually the company that we order from. Sometimes you can order it from Carolina. But either way, it's going to come as 12 molar concentration. That's what it's shipped as. And I need to dilute it for lab. So me as a teacher, I can choose to dilute it to whatever concentration I want. Now, what you don't know is we always choose a higher concentration because that makes the reaction go quicker, and we only have so much time. So we always make 6 molar concentration, and it makes the reaction go much quicker. That way we finish the lab. The lower the concentration, the longer the reaction time. We'll learn that in kinetics. That's chapter 14. So concentration is directly related to reaction time. Now, so my equipment, I've got a 500 milliliter graduated cylinder. Keep that in mind as I'm doing my dilution here. Your equation for dilution is M1 times V1 is equal to M2 times V2. So think of this as in the beginning. Think of this as in the end. Now there's 2 parts to doing the dilution. It's the calculation part and the actual creation of the dilution. Okay? So there's a skill there for actually creating the dilution, but then there's also a side where you have to calculate it, and you kind of have to combine the 2 thoughts to really understand what's going on. Now, once again, I have HCl, and it comes as 12 molar concentration. I want to dilute it to 6 molar concentration. That's typically what you see it as. So in the beginning, what's my concentration? 12. So I'm going to write 12 here. In the end, I just... Holy cow, was that Officer Garrett? All right. I desire to... Wow. The end concentration is going to be 6. Now, in the end, what volume do I have? I have 5. Hello, y'all are going to miss it. I'm going to have 500 milliliters of... Now, you can leave this in milliliters or liters because it's going to be a ratio and the units are going to cancel anyway. So 500 milliliters. So what's X going to be? 250 milliliters. So I just solved this mathematically, but from this mathematical expression, can you actually make the solution? So it's saying 250 of the 500 is the acid, so what's the rest going to be? Water. Now, I would probably put the water in first, and then I would put the acid in. Have y'all ever heard do as you ought to add acid to water? Water? Yeah, you have, because I said it in your class. Water. Now, it's not such a big deal when you're diluting acid, but what you'll find is the dissolution of acid tends to be an exothermic process, and it can change as your acid changes. And HCl will make the graduated cylinder pretty warm, but sulfuric acid, holy cow. You've been working with car batteries? All I know is one time I diluted sulfuric acid and it started boiling. Boiling. So awesome. No, no. So I don't use that anymore. So HCl doesn't, this solution must not be as exothermic as sulfuric acid. No questions. I'm not taking questions. All right, moving on. Types of concentration. Y'all, this is real hard. Real hard. I think you're only going to learn about molarity in this unit. So moles of solute over liters of solution. If you don't know about that by now, I'm looking at everybody. I'm going to hurt you. Not really. If you don't know that by now, that means you didn't do your summer work. All right, moving on. Titrations. Do I really need to work out a molarity question? Please don't. Number. Hey, Christian. Number, which one was the titration one? Number 81B. I'm about to fly through this, so just listen. 81B. I've got 2 HCl plus MgOH2 yields salt MgCl2 plus water. Now, I know in the problem, if you were to read the problem, it tells me I start off with 2.87 grams of base. Now, by the way, this is the acid and this is the base. Y'all should know that. And there's one other piece of information I know. There's 0.128 molarity of acid. So I'm looking for liters of acid. So molarity of acid equals moles of acid divided by liters of acid. They all have to be the same substance, okay? Now, if I have this, which I do, and I have moles of acid indirectly, because I have grams of base, then I can stoichiometrically convert from grams of base to moles of acid. Then I indirectly have that. So then I can solve for liters of acid. Y'all with me? So .87 grams of base, if I were to do the molar mass, 58.32 grams of base, mole to mole, for every 1 mole of base, there are 2 moles of acid. And then if I were to solve for that, 0.0984 moles of acid, guess where that goes? Guess where this goes? Did you just say meow? All right. So guys, we did dilutions, titrations, molarity, and redox all in one day. All right, bye-bye, Kelly. Y'all say bye, Kelly.
Bye. It was so boring without you.
Wow.
Yeah, I feel unnatural today.
Wait, was I recording that?